friends. Hello, hello, hello. Welcome to AP Calculus. I am excited that we are here finally back together again. It was an interesting spring. Summer, you probably didn't do a whole heck of a lot. I am looking forward to hearing what you guys did. But in the meantime, just a quick video on kind of what to expect. So first of all, there's no notes here for you here that you need to take, whatnot. Just quick idea of where we're going to. Calculus is divided into really three things. So at least for Calc AB, we have limits, we have derivatives or differentiation, and we have integrals or integration. And so our first little bit, so our first unit is going to be all about limits. So that's going to be our unit one. And then derivatives, that's going to be a lot of what we do in 2 and 3. And then we're going to come back in a little bit. We'll see some of this in 5. Integration, this is going to be 4 and 7. And we'll also see 6 is kind of a combination of in both of these. So kind of gives you an idea here. We're going to deal with this idea of limits, and then we're going to use that to branch off into these other two areas of derivatives and integrals. So now the idea is where do they come from? So back in the 1700s, we had two mathematicians, and amazingly, they were actually dealing with it at different places. And they ended up coming up with this idea of calculus. They called it advanced algebra, but it's what we call current day calculus. Now, Newton was the first one to publish it, but some people believe Leibniz actually may have done it before Newton. At the very least, we know they did it simultaneous. It's just Newton was the first one to actually get it fully published, which is why a lot of people will say Newton is the father of calculus. But both these guys really did everything. So, I mean, we're just kind of walking in their footsteps. So here's essentially what's going on here. Calculus is based off of pretty much two problems. So to begin with, anytime you have a curve, you can have two lines and a line that connects it. So this is the idea of what we call a secant. So if we think back to circles like that, a secant line is really nothing more than some line that goes through it at two different points. So a secant line is a line that connects or intersects a circle or a curve or any sort of graph at 2 points. Now, a tangent line, well, that would be where it only intersects at 1 point. So if you think back to when we talked about circles before, a tangent line intersects that circle at 1 point. So it doesn't go all the way through, it's just 1 point where it actually pretty much, oopsies, not what I wanted to use there. There's 1 point where it actually kind of hit and connected the dots a little bit. So secants goes through 2 points, tangent lines go through 1 point. So what ended up happening here is for mathematicians, they started looking at this and thinking, what if we wanted to figure out just the slope between any 2 points on that graph? So they ended up taking this idea and they took 2 points. So you can kind of see these 2 points on here. You got point 1, just x sub 1, y sub 1. That just means the x and y coordinate of the first point. X sub 2, y sub 2, that's just the x and y coordinate of the second point. So, and for some mathematicians, they don't like using y, they use f of x. And technically that should have been f of x sub 1. And f of x sub 2. That 1 and 2 should have been in the parentheses there. So that's probably not the greatest thing in the world. We're just going to bleep that out there so you guys don't see that. So you can't even see it. Totally gone. So whether you use x sub 1, y sub 1, or x sub 1 and f of x sub 1, doesn't matter. They're all kind of the same thing. But what mathematicians started looking at and going, they really wanted to try to get away from using y. So they like everything to be in terms of one term. So what you see here is this idea of a triangle. Now this triangle right here, this is the Greek letter delta. So some people call this delta x. Back in integrated 1, when we were first introduced to this idea of delta x, we thought of it as the phrase change it. So delta x really means the change in x. It means the difference in x. It means how far we travel from this x to this x. So instead of doing x sub 1 and x sub 2, we can write everything in terms of just a single x. So x plus the distance in that x value that we went from left to right. So then this one right over here would be f of whatever that x plus that distance is. So now we have everything that's essentially in terms of one point and one distance. So as math people kept going through there, they said, all right, well, let's go ahead and let's take that idea and let's try to figure out the slope between those 2 points. So if you think back to integrated 1 here, and again, you guys have done a lot of these here, they started looking at essentially just this idea of a slope triangle. So how do we figure out the slope of that distance? And you guys learned that is the change in x over the change in y. So this was really nothing more than the change in x over the change in y. So then we learned then that the slope was the difference of rise over run. In other words, it's the change in y, the difference in our y values over the difference in our x values. And so that's where this formula that we learned back in, again, integrated 1, 8th grade, this idea of y2 minus y1 over x2 minus x1. Or if you wanted to, you could use these values right here, which honestly we kind of like a little bit better. Because if we use these values, we're able to simplify it a little bit. And when we simplify f of x plus delta x minus f of x, and when we simplify, what ends up happening here is you end up coming up with those x's on the bottom cross out, and you end up coming up with what we call the difference quotient. And you guys saw the difference quotient a little bit back in pre-cal. So not anything totally brand new. You saw it back in pre-calculus a little bit, but we didn't do much with it at that point in time. There really wasn't much reason to do much with it. But it was this idea of f of x plus delta x minus f of x all over delta x. And it was a way for us to be able to figure out the slope of any secant line. So the way to figure out any slope when we knew we had 2 points, because we could always use that delta x to find the distance between those 2 points. So what our good buddies Newton and Leibniz did is they said, oh, that's interesting. What if we started taking this distance and over time, we made this distance, we made it closer. So maybe this distance right here was 5 units long. Maybe now it was 2 units long. And what they ended up saying there is, what if, just for the sake of argument, what if we let this distance just keep getting closer and closer together, so eventually the 2 points are no longer 2 points. Those 2 points, essentially, they lie on top of each other. And if those 2 points were lying on top of each other, then that distance between them would be 0. In other words, our slope of f of x plus delta x minus f of x all over delta x. So that formula that we essentially have for finding out what the slope is, if we take that delta x, where these two end up lying over the top of each other, we end up getting something that is equivalent to 0 over 0. And we've said for the longest time, we can't divide by 0. It's impossible. We call this idea of 0 over 0, we call that indeterminate form. In other words, we can't determine the value of something when this happens. But the idea is, maybe if we manipulate it enough, maybe there's a way that we actually can do it. Maybe there is a way that we actually can still figure out the slope of a tangent line when the 2 points are on top of each other. In other words, if slope is the average rate of change, maybe there's a way when the 2 points are the same, maybe there's a way we can figure out the rate of change at a moment, at a particular instant. We call that instantaneous rate of change. So this right up here, when we're dealing with the slope between 2 points, we call that average rate of change. But if those points are the same exact time, I am not the world's best speller in the world. Rate of change. Maybe there's a way we can look at this as finding the rate of change at a given moment. So slope is average, but this idea of finding the slope at a point, that's instantaneous. In other words, we can figure out how fast or what the speed or the rate something is changing, and not just of a curve, but of anything. This idea here of learning to find the slope at a single point, learning to figure out the instantaneous rate of change, that is the idea of differentiating. So that's what a derivative is. Derivatives are nothing more than figuring out the instantaneous rate of change. In other words, it's the same thing as finding the slope of a tangent line at a given point, which is what a tangent line is. So in other words, for us then, a derivative is instantaneous rate of change, where the slope between 2 points, we call that the average rate of change. And all together, this is called the tangent line problem. So the first part of calculus is dealing with this idea of a limit. We'll get into that. But this idea that says we'll use limits to help us figure out this instantaneous rate of change, well, we call that a derivative. So that's the first big problem where calculus kind of had its basis in. The second one honestly deals with the area of a rectangle. So in rectangles, nothing more as base times height. Or if we look at it in terms of on a rectangle, it is the x value and it's the y value, which we can also say is the same thing as f of x. So we are really good at finding the area of rectangles or of triangles or trapezoids. But what happens if I got a funky shape? If I got a funky shape like this, there is no rectangle that would fit it. For instance, if I were to build my rectangle here, well, my area would be too much. We call that an over approximation. So instead of that, what if we build our area down below? Well, that would be an area that's too little. You can see how it doesn't cover the entire thing. That would be an under approximation. There is no way to use some geometric figure to figure out what the area is of this curve. So that's where math people, our good buddies Leibniz and Newton, they started looking at this going, well, maybe there's something else we can do. So here you go, you see how the area is too much and too little. So they started looking and going, what if we broke it up? What if we made it a whole bunch of rectangles, like for instance, 2 rectangles? If we did 2 rectangles, well, the area would be a little bit better. But if you notice, I'd still have a little bit too much right over here. Still be an over approximation. If I make more rectangles right here, all of a sudden, it's a little bit better approximation. And what if you made even more rectangles? In other words, what if we were to take these rectangles and make them even smaller? What if I were to take these and maybe I split them in half a little bit? So what if, let's see here, what if I go like this and I take that rectangle and I maybe make it even smaller? So then all of a sudden what happens here is my rectangles the amount of area outside is starting to be less and less and less and less. And so now the more rectangles we add, so now I went from 5 rectangles to 10 rectangles. The more rectangles we add, it starts to get closer. And what if I take these 10 rectangles and I split them again? So now instead of going from 5 rectangles, I went to 10. If I split them again, I'd have 20. If I break this thing up by 20 rectangles, it'd be closer. What if I split them again, and then I'd have 40 rectangles? If I use 40 rectangles under this curve, they're really, really small, but I'd start to get even closer. What happens if I have an infinite number of rectangles underneath this thing? In other words, I still have these heights, but if I had an infinite number of rectangles, I would no longer have a rectangle. I'd have essentially a whole bunch of line segments stacked up, side by side by side. And if I had an infinite number of these line segments side by side by side, I could actually make the exact curve. The problem is, if I had an infinite number of these rectangles, that means the base of each of those rectangles would actually be 0. Well, friends, height times base is area, but if my base is 0, height times 0 would be equal to 0. A line segment has no area, it's just 0 because there's no base. But we're saying that if we were to split them up infinitely, all these infinite zeros somehow would add up to be in theory, the area underneath that curve. Well, friends, that right there, that's called the area problem. The area problem is what integration is, or specifically what a definite integral is. So the area or displacement under a curve is called the definite integral. And that's the third big thing that we'll be learning about here in AP Calculus. So again, to kind of recap here, and I know this was probably a lot to take in here at the beginning, but it just kind of gives you an idea of where we're going. We're going to start off dealing with limits. And we're going to use this idea of limits to help us figure out the instantaneous rate of change, to help us figure out the area, units 2, 3, and a little bit of 5. And then we're going to use this idea of limits to help us figure out how to deal with integrals. That's units 4, a little bit of 5, and 7. So that's kind of where we're going this year. And then the other unit that wasn't included was unit 6. And unit 6 is going to be kind of combining both of these ideas into something called a differential equation. So that's what pre-calculus is. Limits, derivatives, and integrals. So it's going to seem like dividing by 0, infinite number of zeros. It seems weird. It seems like a lot. It's not that bad at all. And we'll take our time. We'll walk through it together. It's going to be a fun journey this year. And friends, I can't wait to share it with you. So anyways, that just gives you an idea of kind of what to expect. And we'll start diving in a bit more in detail here in a little while. Have a great day.